All right, so last time we discussed how to find the electric field created by a group of point charges, right? So the theory is this. First of all, we learned for a point charge, right? For a point charge, the magnitude of the electric field is always this. Right, K is a constant, Q, okay, let's use a big Q. But it doesn't really matter. And this big Q is the source charge, right? The R is the distance from the source charge to the point you want to calculate the electric field, okay? That's the magnitude. And the direction, our convention is this, right? So we can draw the electric field, okay? If it's a positive charge, the electric field at any point, okay, the arrow you're going to draw is going to be away from the charge, right? So for example, if I want to draw the electric field at this point, it's going to be in this direction. If I want to draw the electric field at this point, it's going to be in that direction, okay? So magnitude and direction, right? And then the only difference for a negative source charge, okay, magnitude is still this equation, okay? And then positive, right? Always positive because there's an absolute red sign key. And the direction, our convention is that the direction of the electric field is toward the charge, okay? So if I want to draw the electric field at this point, that's how I'm going to draw the electric field, okay? The vector. The electric field at this point, I will draw the direction, okay, toward the charge, okay? So that's our theory for a point charge. Then we use this superposition principle, right? If there is a group of point charges and I want to find the electric field at a certain point created by all these source charges. So all I need to do is just use this theory to find the electric field created by each single charge and then add them as vectors, right? So for example, if I have Q1, Q2, Q3, etc. Okay, I want to find a positive source, negative, positive. I want to find the electric field at this point. What do I do? Use that theory, okay? Find the magnitude at this point created by Q1, Q2, and Q3. Draw these arrows, right? Q1 positive, so the direction of the electric field is going to be in this direction, U1, right? And then the direction of the electric field created by Q2, E2 is going to be toward Q2, right? So I'm going to draw the electric field this way. Now what about these Q3? Q3 is positive, so it creates an electric field away from it at this point. Okay, find these three numbers, break them into X, Y, Z components, combine all these components, right? Add X components together, Y components together, Z components together. Then at the end, you combine these components to find the net electric field at this point, magnitude and direction, okay? So as I said, once you have done this, right, this is the hard part. Once you have done this, then if I place any test charge at this point and I want you to find the electric force on that test charge, okay, that's going to be easy, right? I'm just going to rearrange the definition of the electric field, right? This is definition of electric field. Rearrange it, you would get this electric force at any point, okay? It's going to be the test charge multiplied by the electric field at that point, right? The electric field I have already calculated, okay, using that fundamental theory, okay? That's the hard part. Once you have done that, this is the easy part, okay? All you need to do, again, when you use this equation, magnitude is going to be everything positive, multiply them together, right? Direction, we said that you need to take a look at the direction, the sign of the test charge, right? So if there's an electric field at this point in that direction, okay, I'm going to place a test charge, okay? This electric field is created by some source, okay? I already calculated, okay? I'm going to place a positive charge here, test charge Q0. What is the direction of the electric force? Well, the force is going to be, because this is positive, the force is going to be in the same direction as the electric field. That's the direction, okay? Magnitude, multiply these two numbers together, make everything positive, right? The same, if it's the same electric field, right? The same electric field, I calculated the number and direction. Now I place a negative charge here, test charge. I want to find the force this test charge feels. Direction is just going to be opposite to it, because this is a negative charge, right? Magnitude, multiply these two numbers together. Okay, so that's why we define this electric field. And then using this superposition principle, we can, in principle, we can calculate the electric field created by any combination of point charges, right? Even though the work can be really tedious, right? Can take you a lot of time, especially if I want to find out the electric field at every point, okay? But theoretically, we can always do that, okay, right? The next question we want to discuss is this, okay? So this is for multiple point charges, right? Superposition principle, okay? So we have summarized that on the first slide in PowerPoint 3. The question is this, okay? What if we have a continuous charge distribution, okay? We don't have isolated point charges, right? I give you something, okay? And then this whole thing has been charged with a lot of charges, okay? So they're not isolated, okay? And then you can't even count how many charges are on this guy, right? How do you count, right? So in this case, how do we find the electric field created by this thing, okay, totally charged? We still use the same idea, okay, but now we're going to use a different mathematical tool, integral. We don't use a summation. We don't do algebra anymore. We do calculus, okay? That's the power of a calculus, okay? Calculus helps you to deal with an infinite number of elements, right? You can say that there's a infinite number of charges on this guy. I can't even count how many are there, right? Then how do I add them up? You can still add them up, but when you add them up, the summation becomes an integral, okay? So that's the power of this new mathematical tool, okay, invented by Newton. All right, so the idea is this, right? So I can still imagine this guy is made of infinite number of charges, right? So what I'm going to do is this, okay, let's pick this guy. Let's call it Q1, okay? So if I want to find the electric field, still I want to find the electric field at a certain point, like this point. Find the net electric field at this point. Well, I'm going to draw the electric field created by this guy, right? At that point, E1. Then I'm going to do the same thing. I'm going to pick this guy, call it Q2, and then draw the electric field at that point. Right, and I'm going to do the same thing with another point charge I can pick, say Q3, draw the electric field created by that guy. Okay, so the theory is still the same, right? All I'm going to do is just to add all these electric fields together, right? So the net electric field is still going to be the summation of all these E's, right? So we're going to call it EI, okay? Now the problem is this, right? Now you have an infinite number of charges, okay? Then you're going to have an infinite number of these vectors, right? How do you add them? Well, you can still add them, but it just becomes an integral. So that's the notation, right, for an integral. So I'm going to still add all these E's, but now each electric field, it's a vector, okay, comes from an infinitesimal, okay, charge I pick on this continuous charge distribution, right? So I'm just going to change all these notations, right? You still remember these notations we used in calculus. So for all these charges, I'm going to call it dq, okay? So we use this symbol d to represent that it's infinitesimal, infinitely small, okay? It's just a notation. It's still a q, okay? You can imagine it's still a q. It's just like really small, okay? The size of this q is just really small, infinitely small, okay? Then the summation becomes integral. and then the electric field created by dq is going to be called dE. Okay, so that's the idea. Okay, that's the idea. But again, to carry out this integral is definitely going to be harder than adding all these together. Okay, because it's totally different kind of thinking. Okay, so this part is always like one of the hardest parts. Okay, in E&M. Okay, so you should definitely pay attention. Okay, you can watch this video many times. If you don't get it the first time, it's very normal, okay, because it's a totally different kind of thinking. It's totally different mathematical tool, right? I know that you have learned calculus before, but calculus is very abstract, right? If you don't use that, you may already forget like most of it, okay? So that's fine. We're gonna just refresh our memory, okay? We're gonna use some concepts we're learning. We're gonna review them here, and then we're gonna practice several examples so we get used to this different mathematical tool. Okay, all right. So that's the idea, right? That's easy to understand. Okay, okay, I know that. Okay, so that's this is still a summation. Okay, don't be scared by this symbol. This is still a summation, right? Just like now you're adding up an infinite number of very, very small elements. Okay, you have to use a different mathematical tool. You can't just do algebra, right? You don't even know how to do that. Okay, so that's why we're going to practice with some continuous charge distribution in this lecture. Okay, and before we do that, there are some useful concepts we want to introduce. Again, why do we introduce them? Because they're useful. Okay, you may not use them in your life, so these concepts may be new to you, but they're very useful in this part when we calculate the electric field created by continuous charge distribution. That's why we define them. Okay. All right. Let's see. These concepts are called charge densities. Okay. So we're going to see why they're useful, but now let's first define them, okay? So if you have a one-dimensional charge distribution, okay, like a line, very thin line, a very thin rod, and it's been charged, that's what we're going to do next. So you can define this thing called a linear charge density, which is the total charge divided by the total length. Okay? So sometimes the problem is going to give you the numbers, right? Okay, a rod has been charged like 5 coulombs. It has a length 2 meters. Okay, just divide them. Okay, if you don't have numbers, you can still use symbols. So we're gonna do a lot of things with symbols in physics. You definitely need to get used to that, right? And you have seen that in physics 1. Okay. So this is called linear charge density. Okay, we define for one-dimensional charge distribution. And then if we have two-dimensional charge distribution, we can define something called surface charge density. So this is a Greek letter lambda, so we use a lot of Greek letters. Okay, the surface charge density is usually represented by this symbol sigma. Okay, sigma E, the charge is still the total charge divided by the area. Right. So, for example, you have some like a disk. Okay, it has a lot of charge on it. Okay, so you can define, like I have a disk. This guy has a lot of charge on it. Okay, I can define this surface charge density. Just divide the area by the charge by the area. Okay, of course, if you have a three-dimensional charge distribution, you can define this thing called a volume charge density, which is denoted by this Greek letter rho. Okay, so that's going to be the charge divided by volume. Okay, so why are they useful? Think about that. Okay, you can compare them with the mass density we have been using, or we just call it density. Right? This thing is useful, right? Because it can be a property for a certain substance, right? Like water has like pure water, the density of pure water, you can look it up, right? 1,000 kilograms per cubic meter. Okay, so it's a constant. Okay, you can use that to calculate the mass of a certain water, right? If I give you like a water, I tell you the volume, right? Like 2 cubic meters, okay? And I want you to calculate the mass of this water. Easy, right? I rearrange this equation. I look up the density of the water and then multiply that by the volume of the water you give me. I find the mass of the water, right? So that's how we use this, why this mass density is useful, okay? These guys are also useful when we want to calculate the charge on a small segment of the charge distribution we're going to see. Okay, so that's why we define them. Okay, so just compare them with the mass density. Okay, to help you get used to get familiar with these three guys. Okay. Okay, so now we're gonna take a look at a real example. Okay, we're gonna start with the one-dimensional charge distribution, like a rod. Okay, to take a look at the image and the question on slide 3. A uniformly charged rod has a length L, so everything symbols, okay, total charge Q. We want to find the electric field at a point P with a distance D from the center of the rod, okay, so let's see. So all symbols, right, we're not using any numbers. And we're going to do some derivation using calculus. All right, so let's see. This is a rod, okay, so it has been charged with positive charge, and then the total charge on it is big Q, and then it has a length big L, okay? Now we want to find the electric field at the point P, so this is point P, say, and it has a distance. So it's along the axis crossing the center of this rod, and then it has a distance D. Okay, so this is the point P from the center of the rod. So we want to find the electric field at this point, right? We can still use a superposition principle, right? But now we're dealing with a continuous charge distribution, so the sum is going to become an integral, right? Because you can't even count how many charges on this rod, okay? It's continuous charge distribution. It's not isolate like 100 charges on it, right? So the idea is still the same, right? I'm going to still pick a very, very small, infinitely small charge on this rod, okay? And then I'm going to draw the electric field created by that very, very small charge, okay, and then go from there. Okay, I can still treat that very, very small charge as a point charge, right, which is straightforward. So for example, if I pick this guy, okay, doesn't have to be the very top, okay, just pick any random piece. So I pick a very, very small charge right here. So how do I find the electric field created by this small charge? Well, first of all, I can draw the direction, right? So if I draw the direction of the electric field created by this guy, okay, forget about everything else. There's a positive charge here. What is the electric field created by this positive at this point P? Well, okay, if I connect these two lines, then this, it's gonna be the electric field created by, right? Because that's the theory we learned, right? Positive, the electric field is going to be away from it. Now, what about the magnitude? Magnitude is still going to be this, right? Ke times whatever the charge is, okay, divided by the distance. Now, the distance is going to be this. Okay, I don't have a numbers. That's fine. Okay, we're working with these symbols. Okay, so that's how I would find out the magnitude and direction of the electric field created by this guy, right? Right at this point P, okay? But I'm not done yet, right? I want to find the electric field created by this whole rod. So I have to find the electric field created by every single infinitesimal charge, okay? The electric field created by every single infinitesimal charge at this point, add them together, right? So there will be like an infinite number of electric field I should draw here, right? But I noticed that there's a symmetry I can use here, Okay, so for example, if I pick another charge like down here on the lower half, which has the same distance to the center as this one I just picked. Okay, so say if I call this Q1, I call this Q2. Okay, now how do I draw the electric field created by this guy? Well, again, first connect these 2 points. All right, and then you can draw the electric field. Okay, this is still positive. I'm going to draw the electric field away from it. So that's going to be E2, right? So you should notice that first of all, E1 and E2, if I pick these 2 little point charges, E1 and E2, they should have the same magnitude. Why? Because the electric field is always going to be this, right? Ke Q over R squared. Okay, so they're both infinitesimal, very small charge, so they carry the same amount of charge. Now Ke is a constant. Distance. Well, I picked these 2 charges so that their distance to the center is the same, right? Remember, that's how I picked the Q2. So they will have the same distance to the center. Then you take a look at these 2 right triangles. They are identical, right? They share the same side, D. They also have another side which is equal, okay? Of course, the hypotenuse is going to be equal, right, from the theorem, okay? Pythagorean theorem. So that means this R is going to be the same, right? Whatever this number is, this is going to be the same, right? 5 meters, this is going to be 5 meters. 10 meters, this is going to definitely be 10 meters. So E1 and E2, they will have the same magnitude, right? They will have the same magnitude. And because these 2 triangles, they're identical, so these 2 angles, they're going to be identical, right? If this is alpha angle, this is going to be alpha, or theta, whatever you call it. Then that means this is going to be alpha, this is going to be alpha. That means if you break this E1 and E2 into X and Y components, there's one component that's going to be cancelled, which is going to be Y, right? Because what is the Y component from E1, right? You're going to draw these vertical component down, right? So this is E1Y. What is the component, Y component of E2? Well, you're going to draw the component up. Okay, so how do you find these 2 components? Well, E1Y is going to be E1 sine alpha. E2Y is going to be E2 sine alpha. You see that? All the numbers are going to be equal. E1 is going to be equal to E2, and alpha they're going to be equal. So these 2 components, they're going to cancel, right? And then their X component is going to add, right? Because X component is going to be this, right? If you break this guy into X, this is going to be E2X. And then you also do the same for E1. This is going to be E1X. Okay? And again, you can also find out that E1X is going to be equal to E2X, right? But anyway, the idea is this. From the symmetry on this problem, so any electric field I draw from an arbitrary infinitesimal charge on the top half, I can always find another infinitesimal charge on the bottom half, okay, which has the same distance to the center of the rod, so that the Y components of these 2 electric fields cancel out exactly, right? So for every single infinitesimal charge on the top half, you can always find a matching infinitesimal charge on the bottom half, which cancels the Y components. Okay, so these 2 Y components, they're going to cancel out exactly. Okay, so what is the result? The result is this. If I want to find an electric field at this point, and I'm going to add all these contributions from every single infinitesimal charge. Okay, true, it's going to be a lot, right? Even a million or billion. But it doesn't matter. At the end, one thing I'm sure is that all Y components I can cancel, right? So the net electric field at this point is only going to be in this direction, right? Because remember, at the end, you're going to add all these vectors together. 1 million, 1 billion, doesn't matter. But you can always pair them up very carefully. So for each pair, Y components cancel. Y components cancel, right? So all these Y components cancel, right? So at the end, you're gonna have like a million or a billion X components left, but that's fine. I can add them, but because they are all in the same direction, which is easy, right? You can literally add them, right? They are just in the same direction. You can literally add these numbers, right? So you see that we're using this symmetry, we actually reduce this problem to the electric field to a scalar, okay? Because we only need to worry about the X component. All these Y components, they're just gonna cancel out, okay? You don't need to worry about that, okay? So that's the first conclusion we drew. So in this class, okay, in most of the problems, okay, you can always use the symmetry to remove one of these components to make the integral from the vector integral to scalar integral. You only need to integrate the components in one direction, okay? So that's our conclusion, okay? So this rod is here, carries positive charge. So if I want to find the electric field at a point here, okay, which has a distance d from the center of the rod, first of all, without doing any calculations, I know that I can draw the net electric field in that direction if I call that x direction, because I just figured out using all this, using the symmetry of this rod, all y components cancel, right? So next, I'm just going to focus on the x component, okay? So the net electric field only has x component, right? So I can write it this way. I hat plus 0 j hat, right? So I don't need to worry about this y component, okay? So I hat and j hat, they're again notations. I hat is the unit vector in x direction, j hat is the unit vector in y direction. All right, then how do I find out this guy? So now the question is this, right? I only need to find the x component of the net vector, which is just going to be, again, the sum of all these x component of each vector, right? Now, because there's an infinite number of infinitesimal charges here, there's an infinite number of e's here, right? You can have E1, E2, E3, E4 until like E a million, E a billion, right? So this guy is going to become integral. Now I'm going to use this notation, this new notation for calculus, right? So I'm going to call each electric field dE, okay, to indicate that it's a very, very small electric field created by a very, very small, infinite small electric charge, okay? So I only need to find the x component, okay? So now the question is this: how do you find expression of this guy, right? You still need to integrate this. So you need to find an explicit expression for this guy so you can integrate that, okay? So that's what we're going to do next. So how do I find this dE x, okay? So now I'm just going to pick a dq, 1q, okay? Because I know all the y components are going to cancel. So let's say I pick this guy, okay? Now I'm going to call it dq. I'm going to use all these fancy notations in calculus, okay? dq means it's still a charge, infinitesimal, infinite small, okay? So I'm not going to call it like a usual q. I'm not going to use a symbol q. I'm going to add a d in front of it, okay, to remind myself this is a very special q, infinite small. Now this guy, I'm going to erase this. So I'm going to focus on this dq because I already know the electric field only has x component. Now what is the electric field created by this guy? Right? Okay, I just did it, right? The electric field is going to be in that direction. Now I'm going to call it dE, okay? I'm using all these notations in calculus, okay? So why do I put a d in front of E? Well, that just means it's an infinitesimal electric field. It's created by an infinite small charge, okay? So this is a totally mathematical concept. Now remember, I only need to find expression for dx, right? So you can still do vector analysis, right? This is still vector, okay? You break it into x and y, right? We just figured that y components are all going to be cancelled, right? This y component is going to be cancelled by that charge, so I don't need to worry about y component. So let's just draw the x component. So the x component is this, right? So this is dEx if you break it into x and y component, okay? Now, how do I find the expression for dEx, okay? Well, okay, of course, if I have the expression for dE, okay, I would just write this. dEx equals dE times, if this angle I call it alpha, or whatever you want, right? So it's going to be cosine alpha. And of course, this alpha is going to be equal to this angle, right? They are the same angle, all right? So this is the expression for dEx, right? So that's what I can plug in, right? So this guy is going to be equal to dE cosine alpha. Okay, I still don't know how to carry out this integral. How do I integrate this, right? There's a dE, there's cosine alpha, right? And they're two different variables, okay? If I have like a function and then with the same variable, I can integrate that. For example, okay, if I integrate 2x squared plus x dx, you know how to integrate that, right? You have done that, okay? But this is different, right? Okay, the thing I want to integrate is dE, but I have a function cosine alpha. So my goal is this. I want to find another new expression so that I can write everything in terms of one variable. This variable can be x, y, z, or whatever you like, right? But I want to make sure this expression only has one variable, okay? So that I can integrate that, pretty much like this, okay? So how do I do that? Now, first of all, dE, let's find the expression for dE. Okay, dE is still the electric field created by dQ, right? So it's an electric field created by a point charge. I can still use the theory we learned for a point charge. What is the theory we learned for a point charge? This. The electric field created by a point charge, the magnitude equals Ke times the amount of this source charge divided by the distance squared. Okay, so I can still do that here. Now it's just the notation is a little bit different, right? The symbols are a little bit different. How do I find the expression for dE? Well, that's going to be Ke times the amount of charge. What is the amount of charge? dQ. Okay, I don't have a number. Let's use the symbol. It's going to be dQ, and it's positive, so I don't need the absolute value sign. Divided by r squared. Okay, so what is this R? Again, this R has a definition. In physics, everything has definition, right? That's why I like it, okay? I don't need to guess or define things or try to understand these symbols, okay? Using my own judgment. Everything has a definition. R is defined from the charge to the point you want to calculate the electric field, okay? So this is still R. Okay, so that's the expression for dE. Okay, I found an expression for dE. What about cosine alpha? Cosine alpha, you can also find an expression, right? Remember, this alpha is the same as this alpha. So this alpha angle, if I want to find an expression for this alpha, that's going to be this. Cosine alpha is going to be adjacent over hypotenuse, okay? So it's going to be whatever this d is. So this d is different from the differential symbol d, okay? So don't get confused. This is a real d, a distance, okay, divided by r. Okay, so let's see if let's put them together. Okay, first. So what I get is they're going to be this: Ke dq over r squared, and then times d over r. Again, this d is different from this d. Okay, this is one symbol. dq is not d times q. Now, well, I still don't know what to do, but at least I can combine them, right? I can combine this r cubed squared and like a cubed, right? So I can get this. And I can also take this Ke and this d out, right? Because they're going to be constant in this problem, right? So let's do this. So let's see. So I'm going to put Ke out, put this d out, right? So what do I get? I still get dq at the top. Then I get r cubed at the bottom, okay? So we're getting there. Okay, so now you see that I already pulled the two constants outside this integral. So all I need to do is just work with these two guys, okay? But again, there's a problem, right? I still don't have anything like this, okay? A function with of a variable and then d of the same variable. I have d times q. But now I have a function r cubed, a function of r, right? So I can't integrate this, okay? I still have to reduce this whole thing to one variable, okay? So that's the trick we're going to use. So first of all, let's see. This r is going to be a variable, right? What is this r? The r is going to be this distance, okay? But I can use the symbols in this problem to find this r, right? I can just use a Pythagorean theorem again, right? How do I find this r? Find the expression for this r? Well, I would do this. R is going to be square root d squared plus this side squared. But this side is going to totally depend on where this charge is, right? So this side is not going to be constant, right? This d can be a constant, okay? Like 5 centimeters, right, at the end. But this side is going to change, right? Because remember, at the end, you're going to integrate this dq, the contribution of dq along this rod. So that means you're going to pick a dq here, you're going to pick a dq here, here, you're going to calculate this r, and then you're going to add all these contributions together. Well, of course, it becomes equal. So this side is not going to be a constant. So we have to introduce a variable, okay? So because this is in vertical direction, okay, and we only need the distance from this center to this side, right? So I need this distance. So if I call this the origin, and I set up my coordinate system like the usual, as usual, this is x, this is y. So this distance is just going to be the y component, y coordinate of this charge, right? If this guy is at y equals 2 centimeters, that just tells me the distance from this charge to the origin is 2 centimeters, right? So whatever this y coordinate is, it's going to be just the distance between this charge and the point. And that's the distance I want if I want to use the Pythagorean theorem in this right triangle, right? So that's just going to be the y squared I put here. So this y is a new variable I introduced. D is not a variable, okay? It's a constant, right? It's going to be given. We use a symbol for that, but it's not a variable in this problem, okay? So that's going to be the expression for r. So, okay, I got rid of this r, okay? But I introduced a new variable, y. So if I put this expression here, I still cannot integrate that, right? Because I have dq with the function of y, right? So I didn't solve the problem, okay? So the way to solve the problem is that if I could write dq in terms of y, then problem solved, right? So you will have like a function y and then dy, you can integrate that. It's like the x function I just wrote, right? So how do I write this dq in terms of y? So that's a trick we're going to learn this part. That's why this linear densities are useful, okay? So let's take a look at this, how we can write this dq in terms of this lambda e and this y, okay? So this dq is going to be an infinitesimal charge, right? So very, very small, okay? So let's zoom it in. Okay? So it's a rod, okay? Now I'm going to pick a very, very small element. Okay, it's very small, but I want to zoom it in so you know what's going on here. So this is the charge I pick. So this is dq. Okay, it's very, very small, but it still can have a very, very small size, right? Very, very small size. Okay, so this small size in y direction, and it's very small, so that's why our notation is going to be dy. Okay, very small. So now my question is this: how do I write this dq in terms of dy? Okay, so what you can do is this. You're going to divide the total charge by the total length, right? And then multiply that thing by the width, okay, the length of this very, very small little piece I pick. Okay, then you multiply them together. You will get the charge on this very, very small piece. Okay, so to help you understand why that is true, let's just use some numbers, right? So say I have this rod, like a charge is 10 coulombs, okay, and the length is 2 meters. So now I'm going to ask you, what is the charge if I pick like a 0.0002 meter segment on this rod, and I want you to tell me how do you find the charge on that segment. Well, you would do this, right? I would just divide the total charge by the total length and multiply by the length you give me. You want me to find this very, very small length, right? The segment, very, very small segment, the amount of charge on this very, very small segment. I'm going to divide the whole charge by the whole length, okay? And then multiply that thing by the length I'm interested in. Okay? Okay? So this thing is just the charge divided by length. That's the linear charge density we defined before. So that's why it is useful. And this dy, again, it's a symbol for infinitesimal charge, infinitesimal length, okay? So we don't use these numbers, but you can think of this dy as like 0.000000001 meter or something like that. I'm still asking you to find the amount of charge on a very, very small piece I pick on this whole rod. So of course you're going to do this, right? Divide the total charge by the total length, multiply this thing, the density, with the length of this very, very small piece I pick. Even though it's very small, that's how I'm going to calculate the charge on this very small piece. Okay? All right? So we're done. So dq, I can write it as linear charge density times dy. Of course, this linear charge density is going to be the total Q divided by the total L, right? So if it has a total charge L and a total charge Q, total length L, that's what I'm going to do, right? But I can use this symbol. Now let's put everything together. I'm going to put everything together. So what do I get at the end? I get this. So I'm still working on this integral. Don't forget what we're doing. So I get Ke d. Now dq, I wrote it as lambda e dy. Now this r cubed, it's going to be d squared plus y squared square root to the power of 3. So it's going to become this thing to the power 3 halves, right? So that's one more thing I can pull out, right? This lambda e is still going to be a constant. It's going to be a number. It's not going to be a variable. So I can pull it out. So I would get Ke times the distance times lambda e dy over d squared plus y squared. Okay, so now you see that this is one variable, a function with one variable. I can definitely integrate this, right? So you don't need to worry about that. We can just look it up in into a table, because all these normal, like regular integrals, they have already been derived. So you learn how to derive them in calculus. Okay, so we're not going to really do that in this class, but we still need to know how to start from the fundamental theory and then reduce everything to an integral of one variable. That's what we're doing in physics. Okay, so now I can find this integral, the answer to this. Okay, I want to find the answer to this integral using an integral table. Okay, so I'm going to look it up. So you can find this integral table. I posted on Sakai. All right. So I posted a So it has a lot of integral, but if you look at this one, so you just want to find the integral which has this form, right? D, a variable over a constant square plus this variable square to the power 3/2 at the bottom, right? So if you look, and this, it's going to be 41, okay? So take a look at 41. So 41 is this, right? Dx over a squared plus x squared to the power of 3/2. Okay, the answer to this integral, it's going to be the variable divided by a squared in front of this square root, a squared plus x squared. Okay? So that's going to be the answer to this integral. But in order to evaluate this integral, definitely, okay, you need the bounds, right? So you need the bounds to plug in this x, right? This variable. What are the bounds? So what is the variable here? Y. Y is a variable. So we need to find the bounds for the y in this question, okay? So remember, this y is going to go, okay, over this rod. So you're going to integrate this y along this rod. So what is the minimum value of y you can get, which is this point? What is the maximum y value you can get on this rod, which is this point, right? What are these two values? Well, if this is the origin, and you tell me the length of this guy is big L, what is the y coordinate of this point? This is going to be -1/2 L, right? What is the y component? What is the y coordinate of this point? That's going to be 1/2 L. Okay? So that means this is going to be the bounds. So I'm going to integrate. So I'm going to add all these contributions from these dq's from this -1/2 L to 1/2 L. Right? So these are the bounds of the y in this integral. Okay? So this integral is going to from -1/2 L to +1/2 L. Okay? So now I can use that integral I just found in the integral table to evaluate this, right? So all I need to do is just substitute the lower bound and upper bound to this answer, and then I can subtract them. That's how you evaluate the integral with the bounds, okay? If you still remember that. All right? So that's going to be our answer. So now I'm going to erase this. Okay, so the answer is going to be this. I still have KE, D, lambda E. Now I would have this. This guy, okay, so I would have, let's replace all the symbols with the symbols we have now. So I'm going to replace A with D, right? So I would have Y over D squared, square root D squared plus Y squared. Now you're going to integrate, evaluate this from -1/2 L to 1/2 L, right? How do you evaluate this integral with the bounds? You're just going to subtract them, right? So this is going to be equal to KE D lambda E, plug the upper bound in, 1/2 L over D squared plus 1/2 L squared, right? Minus, plug lower bound in, -1/2 L. Lower bound D squared plus 1/2, -1/2 L squared, and subtract them, right? So now you see that you can simplify this a little because they actually have the same denominator, right? Because 1/2 L squared, negative positive is going to be the same. So if they have the same denominator, you can just combine this numerator. You have 1/2 L minus -1/2 L. You just get L at the top, right? So at the end, so you will get L at the top, and at the bottom D squared, and then D squared okay? Now you see that, well, we can, this is pretty much it, right? But we can still make this a little bit simpler, okay? So now what we can do is this. I'm going to erase all this. Now let's put this definition of this lambda e in, okay? Or if you don't like lambda e, you can just carry this q over L all the way, right? It's just a definition, okay? We call it lambda e because it's useful. We can just call it a linear charge density. So lambda e is q over L, right? Now let's plug it back in. So this E net x is just going to be ke d q over L. Then we can do some cancellations to make this a little bit simpler. Square root d squared plus 1/2 L squared. Now you see that, well, this L and this L, they can cancel. And this d is going to cancel 1 power of d here. So at the end, the simplest expression I can get is going to be ke q at the top, and then d 1 power of d left, but I still have the square root here. And that's pretty much it, right? That's the simplest I can get. I can't reduce this anymore, okay? So that's going to be our answer. So our answer is this. Well, the rod is going to create the electric field at point P in that direction. X direction, if you call it X. Magnitude is going to be this, okay? So this magnitude was derived using the same theory we learned, still from the point charge, okay, theory, but we generalize it to continuous charge distribution. The summation becomes an integral, okay? Do you need to memorize this conclusion? No, you don't, okay? You never need to do that in physics, okay? What we're doing is that, and you need to know this, how to derive this whole thing, okay? Starting from the fundamental theory. Do this integral, okay? And until you get expression with only one variable so that you can look it up in an integral table. So on a test, I will also give you an integral table. Well, of course, it's not going to be 100 or 200 integrals. I may pick like 10 to 20 integrals for you to use, okay? But what I want you to do is this. You should understand the theory, okay? You should know how to derive it, okay, from the very beginning. Using the fundamental theory for point charge, reduce the integral to one variable, then look it up in integral table, and then put the bounds in, finish the algebra, get the final expression. Okay, that's what we're doing. That's what we're learning in physics. We're not learning how to memorize. We're not learning to memorize all these conclusions so that we can just plug numbers in and get the answer. There's no point doing that in physics. That's not called physics at all. That's called algebra, right? If I don't want you to understand the duration, I just tell you, remember this, put the numbers in, then get the answer for me. This is not physics, right? You don't need to take this class to do that, okay? We're learning physics. We're not learning how to memorize these conclusions. So you never need to memorize these conclusions. You need to understand the theory. You need to show me, you can use the theory to do the derivation on the test. And as I said, this using an integral to calculate the electric field from a continuous charge distribution is always one of the hardest parts in this class. You should definitely need to practice many, many times, okay, to make sure that you understand the theory. You can do everything yourself, all right? I'm going to stop here for this video.